Sleep. You do it every night. You have done it every night of your life. And for the overwhelming majority of human history, for the thousands of years that human beings have been thinking carefully and systematically about the nature of the world and the nature of themselves, nobody knew what it was. Not the ancient Egyptians, who built their civilization on the banks of the Nile and developed mathematics and astronomy and medicine and architecture to levels that still astonish the people who study them. Not the ancient Greeks, who gave the world philosophy and democracy and the foundations of Western science. Not the physicians of medieval Europe, who studied the ancient text with exhaustive care and built elaborate theoretical frameworks for understanding the human body. Not the scientists of the Enlightenment, who dismantled those medieval frameworks and replaced them with new ones based on observation and experiment. Not the physiologists of the 19th century, who mapped the nervous system and identified the cell as the fundamental unit of life. Not the neurologists of the early 20th century, who began to understand how the brain generated consciousness and sensation and movement. For all of these people, across all of these centuries and all of these civilizations, sleep remained what it had always been, a daily mystery, present and unavoidable and completely unexplained. They knew it happened. They knew it was necessary. They knew that its absence produced suffering and eventually death. And they had, across those centuries, developed an extraordinary variety of explanations for what it was, and what caused it, and what it meant. Explanations that were, from the perspective of what we now know, almost entirely wrong, and that were, from the perspective of the people who held them, the most reasonable explanations available, given what those people could observe and measure and understand. This is the story of how humanity came to understand what happens when you close your eyes. It is a story that takes place across more than 4,000 years, from the dream temples of ancient Egypt to the sleep laboratories of mid-20th century America, from the speculations of Greek philosophers to the electroencephalograph machines that first made the sleeping brain visible to the outside world. It is a story full of wrong turns and brilliant insights and accidental discoveries and the specific kind of scientific humility that comes from spending years studying something and finding, at the end of those years, that you understand it somewhat better than you did before, but still incompletely, still with enormous gaps that the available methods cannot fill. And it is a story that is, in a very real sense, still unfinished. Because the central question, why do we sleep? What is sleep actually for? What does the sleeping brain accomplish that the waking brain cannot? Remains, in important respects, unanswered. We have learned an extraordinary amount. We have mapped the stages of sleep, identified the brain regions involved, catalogued the physiological changes that occur during different phases of the night. We know things about the sleeping brain that would have seemed like science fiction to the researchers who first began studying it systematically less than a century ago, and we still cannot fully answer the question that lies at the heart of the subject, the question that every serious sleep researcher eventually confronts. Of all the things that evolution might have done with the 8 hours a night that sleep consumes, why did it choose this? But to understand where we are, we have to understand where we started, and where we started is very far from here. The earliest recorded human thoughts about sleep come from ancient Egypt, from a civilization that was already old when the pyramids were built, and that had been thinking carefully about the relationship between the waking world and the world of night for longer than most other human cultures had existed. The Egyptians were, by any measure, a sophisticated people. Their agricultural management of the Nile flood cycle, their astronomical observations, their architectural achievements, their medical knowledge, all of these demonstrate a capacity for systematic observation and careful reasoning that is not in doubt. And their understanding of sleep reflected this sophistication, while also reflecting the specific framework within which all ancient thinking about the natural world operated. A framework in which the boundary between the physical and the spiritual was permeable, in which the visible world was understood to be continuously penetrated and influenced by invisible forces, and in which the events of the night were as real and as significant as the events of the day. For the ancient Egyptians, sleep was understood in relation to the concept of the Bay, one of the several components of the soul or self that Egyptian thought distinguished, a component that was in some sense the personality, the animating essence of the individual person, the thing that made you specifically you rather than some other person. During sleep, the Egyptians believed the BA was able to leave the body, to travel, to visit other places, to encounter other entities, to receive information that was not available to the waking consciousness. The dreams that a sleeping person experienced were not the product of the sleeping brain's internal activity in the Egyptian understanding, but the actual perceptions of a BA that had gone somewhere else while the body remained. This was not a casual or peripheral belief. It was central to Egyptian religious and medical practice. The temples of certain gods, most importantly Serapis, the healing god, whose cult was particularly associated with the interpretation of dreams, maintained facilities called dream temples or incubation sanctuaries, where sick or troubled people could come and sleep in a sacred space, under ritual conditions, in the hope that the god would appear in their dreams and provide guidance about their illness or their problem. The practice of incubation, of deliberately sleeping in a sacred place in order to receive a divine dream, was widespread across the ancient Near East and Mediterranean world, and it reflects a deep and widespread conviction that the sleeping state provided a form of access to knowledge and experience that was unavailable to the waking mind. The medical texts that survive from ancient Egypt, the Ebers Papyrus, the Edwin Smith Papyrus, several others, contain extensive material on sleep and dreams, approached with the same combination of careful observation and theoretical framework that characterizes Egyptian medical thinking generally. The Egyptians catalogued dream types, developed systems for interpreting dream content, and understood certain dream phenomena, including what we would now recognize as sleep paralysis, the terrifying experience of waking to find oneself unable to move, as encounters with specific supernatural entities. The demon Hag, in Egyptian belief, was responsible for the sensation of a weight on the chest during sleep and the inability to call out or move, a precise description of the hypnagogic paralysis that occurs during certain stages of the sleep cycle, explained in terms that made complete sense within the Egyptian understanding of the night world. What is striking, looking at the Egyptian approach to sleep from a modern perspective, is not the wrongness of the spiritual explanations, but the accuracy of the observations. The Egyptians noticed that sleep produced dreams. They noticed that certain dreams seemed to recur. They noticed that sleep deprivation caused deterioration in both physical and mental functioning. They noticed that certain positions seemed to produce certain types of dreams. They noticed that people who were ill slept differently from people who were healthy. These are all accurate observations, and they are observations that centuries of subsequent human thinking would confirm and elaborate, even as the explanations offered for them shifted from the spiritual to the physiological. The world that the ancient Egyptians inhabited, the specific texture of their experience of sleep and night, was also, in ways that are worth pausing to appreciate, profoundly different from the world that most people in the contemporary industrialized world inhabit. They went to sleep when the sun went down, because there was no reliable artificial light that would make staying awake after dark practical for most purposes. They slept in conditions of darkness that most contemporary people never experience. Not the partial darkness of a room with streetlights coming through curtains, but the complete darkness of a world without electricity, a darkness in which the only lights were fire, the moon, and the stars. They slept in temperature conditions that varied with the season and that could not be controlled, which meant that their sleep in summer and their sleep in winter were physiologically different experiences. And they slept. This is something that the historical evidence suggests consistently from ancient Egypt through medieval Europe and beyond, differently from the way most contemporary people sleep. The concept of a single consolidated block of sleep from roughly 10 or 11 at night until 6 or 7 in the morning, which most contemporary people in industrialized societies take to be the natural and normal pattern, is, by the evidence of the historical record, a relatively recent development. The historian A. Roger Kirsch, who spent decades studying the pre-industrial history of sleep, assembled an extraordinary body of evidence from diaries, court records, medical texts, and literary sources, suggesting that across most of human history, people in temperate climates typically slept in 2 separate periods: a first sleep that began shortly after dark and lasted for several hours, followed by a waking interval of 1 to 2 hours. followed by a second sleep that lasted until dawn. This pattern, which Eckhart calls segmented or biphasic sleep, appears so consistently across so many different sources and cultures that it seems to have been the default human sleep pattern for most of history, and its replacement by the single consolidated sleep period that contemporary people regard as normal appears to have been a consequence of the spread of artificial lighting in the 18th and 19th centuries, which made the waking hours of the night available for activity for the first time and gradually shifted the social schedule of European and American life in ways that compressed the available sleep time and eliminated the waking interval between the two sleeps. The waking interval between the two sleeps was, in the pre-industrial world, a recognized and apparently valued part of the night. People used it for various purposes: prayer, conversation with a bed partner, reading if there was a candle available, quiet reflection, sex. The French physician Laurent Joubert, writing in the 16th century, recommended the time between the first and second sleep as particularly conducive to sexual intercourse, on the grounds that the digestion was complete and the body was rested. Various religious traditions structured their nighttime devotional practices around the natural waking interval, and the dreams experienced during the second sleep, which occurs, as we now know, during the periods of sleep that are richest in REM activity, when dreaming is most vivid and most memorable, were probably a regular topic of morning reflection and conversation, in a way that is less common in a world where people typically sleep through the night without interruption and wake with only fragmentary dream memories, if any at all. The ancient Greeks approached sleep with the full weight of their philosophical apparatus, and they produced, as a result, a body of theoretical writing about sleep that was more systematically argued and more explicitly concerned with physical mechanisms than anything that had come before. They were also, as it happens, considerably more wrong than the Egyptians about certain fundamental aspects of the subject, a reminder that systematic argument and empirical accuracy are not the same thing, and that a very sophisticated wrong theory can persist for much longer than a simple right observation, precisely because its sophistication makes it harder to overturn. The central figure in Greek thinking about sleep was not primarily a physician but a philosopher, Aristotle, whose treatise on sleep and sleeplessness, part of a series of short works on biological and psychological topics collectively known as the Parva Naturalia, is the most systematic ancient treatment of the subject we have. Aristotle was, by any measure, one of the most formidable intellects in human history. His works on logic, biology, physics, metaphysics, politics, rhetoric, and poetics shaped Western thought for 2,000 years, and in some domains continue to exert influence today. And his thinking about sleep, while it would be entirely superseded by modern neuroscience, represents a genuine attempt to understand a genuine phenomenon using the best conceptual tools available to him. Aristotle's theory of sleep was built on his theory of the soul and his theory of sensation. For Aristotle, the soul was the animating principle of the living body, the thing that made a living body alive rather than simply a collection of materials, and it had several distinct faculties or capacities: the nutritive faculty shared by all living things, the sensitive faculty shared by animals, and the rational faculty that was unique to humans. Sleep, in Aristotle's account, was a state in which the sensitive faculty was temporarily incapacitated, in which the ability to perceive the outside world through the senses was suspended, leaving the organism in a state intermediate between full wakefulness and death. The mechanism by which this incapacitation occurred, in Aristotle's theory, was related to the process of digestion. After eating, Aristotle believed the heat generated by digestion in the stomach produced vapours that rose through the body toward the head. When these vapours reached the brain, or more precisely, when they reached the region of the heart, which Aristotle incorrectly identified as the seat of sensation, they cooled and condensed, and this cooling produced a heaviness that weighed down the head and eyes and caused the onset of sleep. The purpose of sleep, in this account, was to allow the digestive process to complete, to allow the nutritive faculty to do its work without the competing demands of the sensitive faculty. This is, by modern standards, almost entirely wrong. The brain, not the heart, is the organ of consciousness and sensation. Digestive vapours do not cause sleep by rising to the brain and cooling. The relationship between digestion and sleep is real, but works through entirely different mechanisms, through the release of certain neurotransmitters and the activation of certain brain circuits than anything Aristotle imagined. And yet the theory was not arbitrary or irrational. It was built from observations. People do tend to feel sleepy after eating. The head does feel heavy when one is tired. Sleep does seem to be related in some way to the body's recovery and maintenance processes that were accurate, even if the theoretical framework erected on them was wrong. Aristotle's theory would prove extraordinarily durable. It was incorporated into the medical system developed by Galen of Pergamon in the 2nd century AD, a system that synthesized Greek medical knowledge into a comprehensive framework centered on the 4 humours and their associated qualities, and that would dominate Western medicine for more than 1,000 years. In Galenic medicine, sleep was understood as the result of vapours rising from the stomach to the brain, cooling there, and causing the brain's vital spirit to withdraw from the outer senses, an elaboration of Aristotle's account that added the specific vocabulary of humoral medicine without changing its fundamental structure. The Galenic account of sleep determined how physicians thought and wrote about it for centuries. When medieval doctors discussed insomnia, which they called agrypnia, they diagnosed it in terms of an excess of dry, hot humours that prevented the brain from receiving the cooling vapours that cause sleep, and they treated it with cooling, moistening substances, cold baths, lettuce, the application of cooling oils to the temples, preparations of opium, and the recommendation to sleep on the left side, which was thought to facilitate the movement of digestive vapours toward the brain. When they discussed excessive sleepiness, which they called kataphora or lethargus depending on its severity, they diagnosed it in terms of an excess of cold, moist humours that produced too much cooling of the brain, and they treated it with warming, drying substances and stimulation. The treatments were not entirely ineffective because some of them contained active ingredients. Opium, for example, does reliably produce drowsiness, and because the recommendation to create conditions of quiet, warmth and darkness for insomnia patients reflects genuine practical wisdom about what makes sleep easier to initiate. But the theoretical framework was wrong, and its wrongness had consequences. It directed the attention of physicians toward the stomach and the humours and away from the brain, and it made it very difficult to ask the right questions about what sleep actually was and what actually caused it. The Arabic Islamic medical tradition that flourished between roughly the 8th and 13th centuries, and that preserved and extended the Greek and Roman medical heritage during the period when much of that heritage was lost or inaccessible in Western Europe, largely maintained the Galenic framework while making important observations and additions. Ibn Sina, known in the Latin West as Avicenna, whose canon of medicine was one of the most influential medical textbooks in history, accepted the basic Galenic account of sleep while adding careful clinical observations about the relationship between sleep and various diseases. He noted that certain brain conditions affected sleep in specific ways, that patients with fever slept differently from healthy patients, and that the quality of sleep was a useful diagnostic indicator of a patient's overall condition. These are all accurate clinical observations that point toward a more brain-centered understanding of sleep, even if they are framed within a theoretical system that still located the primary mechanism of sleep in the stomach. The first significant challenge to the Galenic framework came not from medical research specifically focused on sleep, but from the broader revolution in anatomy and physiology that began in the 16th century with the work of Andreas Vesalius, whose detailed dissections of the human body corrected many of Galen's anatomical errors, and continued through the 17th century with the work of William Harvey, who demonstrated that the heart was a pump that circulated blood through the body, rather than a furnace that generated vital heat. Harvey's discovery of the circulation of the blood, published in 1628 in his treatise De Motu Cordis, was important for thinking about sleep in several ways. It demonstrated that the physical mechanisms of the body were considerably more complex and more specifically organized than the Galenic framework had suggested. It shifted the conceptual vocabulary of physiology away from the 4 humours and toward the mechanical model that would dominate the scientific revolution, the idea of the body as a machine, operating according to physical laws, its functions the product of specific physical processes rather than of balanced or imbalanced qualities, and it directed attention toward the brain as the central organ of sensation and consciousness. Since if the heart was merely a pump, the seat of sensation must lie elsewhere. Thomas Willis, an English physician who was one of the founders of what would become the discipline of neurology, made the brain and its associated structures the center of his physiological investigations in the mid-17th century. His anatomical work on the brain, conducted with extraordinary care and illustrated by the artist Christopher Wren, who was then a young man before he became an architect, produced the most detailed account of brain anatomy that had yet existed, and his theoretical work attempted to explain mental phenomena, including sleep, in terms of the activity of specific brain structures. Willis proposed that sleep was caused by a reduction in the circulation of what he called animal spirits, a concept inherited from ancient medicine but reinterpreted in the new mechanical framework, through the cortex of the brain. During waking, the animal spirits circulated freely through the brain's substance, animating sensation and thought. During sleep, this circulation was reduced, either because the spirits themselves were depleted by the day's activity, or because some mechanism redirected them away from the cortex. Dreams, in Willis's account, were the product of residual spirit activity in the cortex during sleep, fragmentary and disordered, because the full circulation was not present to organize them into coherent perception. This is still wrong, in the specific sense that animal spirits do not exist, and the brain does not work the way Willis described. But Willis's framework is significantly closer to the modern understanding in one important respect. It places the mechanism of sleep firmly in the brain rather than the stomach, and it begins to describe sleep in terms of brain activity rather than digestive vapors. The direction of travel is right, even if the specific account is not. The 18th century produced refinements rather than revolutions in the understanding of sleep. The great systematizers of this period, Albrecht von Haller, who produced the most comprehensive account of physiology yet written, Xavier Bichat, who introduced the concept of tissue as the fundamental unit of the body, various others, largely worked within the framework that Willis had established, refining the mechanical account of brain function without fundamentally changing the understanding of what sleep was. What did change in the 18th century was the social context of sleep, the conditions under which ordinary people in European cities actually slept, in ways that would eventually have consequences for how sleep was understood. The spread of artificial lighting, first through the improvement of candle and lamp technology, and then through the introduction of gas lighting in the early 19th century, made the nighttime hours available for productive activity for the first time in human history for a significant fraction of the urban population. The coffee houses that became central to European social and intellectual life in the 17th and 18th centuries introduced a substance, caffeine, that could reliably delay sleep and extend the productive day. And the Industrial Revolution, which accelerated through the late 18th and early 19th centuries, began to impose on workers a schedule of continuous daytime labor, followed by nighttime rest, that was enforced not by the natural rhythm of daylight, but by the artificial clock-based schedule of factory production. These changes, the spread of artificial light, the introduction of caffeine, the imposition of industrial work schedules, gradually transformed the sleep patterns of the people affected by them, compressing their sleep time, eliminating the natural waking interval between the first and second sleep, and creating for the first time a large population of people who were chronically sleeping less than their biology required. They also created gradually a new kind of medical problem, not the traditional insomnia of the classical medical tradition, which was understood as an imbalance of humours, but a new phenomenon that physicians began to call exhaustion or nervous exhaustion, a condition of chronic fatigue and dysfunction that seemed to be related to the demands of modern industrial life, and that would, by the end of the 19th century, be given the name neurasthenia. Neurasthenia was diagnosed extensively in the late 19th and early 20th centuries, particularly in the educated professional classes of Europe and America, the people who, by virtue of their social position, were most exposed to the new demands of industrial modernity and most likely to be seen by physicians. Its symptoms included fatigue, poor sleep, difficulty concentrating, irritability, and a general sense of being worn out, symptoms that we would now recognize as consistent with chronic sleep deprivation. And the response to it, in the medical literature of the period, marks a new kind of attention to sleep as a medical concern, not sleep as a theoretical problem in physiology, but sleep as a practical problem for a large number of real people living in a world that had changed faster than human biology could accommodate. It was in this context, a world of gaslit streets and telegraph offices and steam-powered factories, a world in which the natural rhythms of daylight and darkness had been partially overcome by technology, and in which a new kind of medical concern about the adequacy of sleep had begun to emerge, that the scientific study of sleep began to take its first tentative steps toward becoming a real discipline. The first person to study sleep scientifically, in the modern sense of devising experiments, specifically intended to produce measurable data about what happened during sleep and what happened when sleep was prevented, was not a sleep specialist. There were no sleep specialists because there was no specialty. He was a German physiologist named Ernst Kohlschutter, who in 1862 published a study in which he measured what he called the depth of sleep by determining how loud a sound had to be at various points during the night to wake a sleeping person. Kohlschutter found that sleep was deepest in the first few hours after it began and became lighter as the night progressed, a finding that is, in its broad outlines, correct, and that anticipates what modern sleep research would later establish with much greater precision. Kohlschutter's study was published and largely forgotten. There were no institutional structures within which sleep research could develop, no journals dedicated to the subject, no research programs, no careers to be made from studying it. The physiologists of the mid-19th century had many other, seemingly more tractable problems to pursue: the mechanisms of muscular contraction, the physiology of the sensory organs, the electrical properties of nerve tissue. Sleep remained a daily mystery, familiar and universal and unexplained, waiting for the tools that would make it possible to study it from the inside. Those tools were being developed in the late 19th and early 20th centuries in ways that had nothing directly to do with sleep, but that would eventually make the scientific study of sleep possible. In 1875, the British physician Richard Caton demonstrated that the brains of rabbits and monkeys produced continuous measurable electrical activity, that the brain was not merely a static structure, but an electrically active one, generating signals that could be detected and potentially recorded. The implications of this discovery were not immediately pursued, partly because the technology for recording weak electrical signals was not yet adequate for the task. But the observation had been made: the brain produced electricity, and that electricity could be measured. It would take another 50 years, and the invention of the electron tube amplifier, before the technology existed to make Caton's observation into a practical research tool. And when that tool finally arrived, when a German psychiatrist named Hans Berger successfully recorded the electrical activity of a human brain for the first time in 1924, producing what he called the electroencephalogram, the EEG, it would open a window into the sleeping brain that no one had ever had before. But that is where we are going. To understand where Berger arrived and what he found when he looked at the sleeping brain through the window his invention provided, we have to first follow the thread of human thinking about sleep through the long century between Kohlschutter's sound experiments and Berger's electrical recordings, a century in which the question of what sleep was and what it did began, for the first time, to be asked in a form that science could begin to answer. To understand where Berger arrived and what he found when he looked at the sleeping brain through the window his invention provided, we have to first follow the thread of human thinking about sleep through the long century between Kohlschutter's sound experiments and Berger's electrical recordings, a century in which the question of what sleep was and what it did began, for the first time, to be asked in a form that science could begin to answer. The 19th century was, in many respects, the century in which the brain became the central object of scientific inquiry into human mental life. Before the 19th century, the brain was understood to be involved in sensation and movement, and perhaps in some aspects of higher mental function, but the specific mapping of mental faculties to brain regions, the understanding of how the brain generated consciousness and thought and emotion, remained almost entirely speculative. The century that began with Franz Joseph Gall's phrenology, the theory that specific mental faculties were localized in specific regions of the brain's cortex, and that the shape of the skull could reveal which faculties were most developed in a given individual, and ended with the first systematic investigations of the brain's electrical activity, was a century of transformative, if uneven, progress in understanding what the brain actually did. The phrenologists were wrong about the specific theory. The skull does not accurately reflect the brain's shape, and the brain's organization does not correspond to the faculties that Gall identified. But they were right about a more general principle, that mental functions were not uniformly distributed throughout the brain, but were associated with specific regions. This principle of localization, stripped of the specific phrenological claims, survived the discrediting of Gall's theory and became one of the organizing ideas of 19th century neuroscience. The work of Paul Broca in the 1860s, who identified a specific region of the left frontal cortex whose damage consistently produced a specific kind of language impairment, provided experimental support for localization that the clinical observations of subsequent decades would expand and refine. The implications of the localization principle for thinking about sleep were not immediately apparent, but they were real. If specific mental functions were associated with specific brain regions, then sleep, which affected all mental functions, suspending sensation and voluntary movement, and the higher cognitive functions while leaving the vegetative functions of breathing and circulation intact, was probably not a simple, uniform reduction in brain activity across the entire organ, but something more structured, more organized, with specific brain regions playing specific roles in its initiation and maintenance. This was not a conclusion that anyone drew explicitly in the 19th century, but it was the direction in which the evidence was pointing. The physiological study of sleep in the 19th century was dominated by a question that seems very basic, but turned out to be surprisingly difficult to answer. What, exactly, is the difference between a sleeping brain and a waking one? The ancient answer that sleep was a withdrawal of the soul, or a cooling of the vital spirits, or a suspension of the sensitive faculty, was no longer credible in a world that had accepted the cell theory of biology, the conservation of energy in physics, and the evolutionary theory in natural history. Sleep had to be explicable in physical terms as a specific state of the brain's biological machinery. But what were those terms? The most influential physiological theory of sleep in the second half of the 19th century was proposed by a group of researchers working in the tradition of the newly developed science of physiology, the experimental science of how living bodies function, who focused on the blood supply to the brain as the key to understanding sleep. The theory, developed by several researchers independently and most clearly articulated by the German physiologist Wilhelm Thierry Preyer in 1877, proposed that sleep was caused by a temporary reduction in the blood supply to the brain. When blood flow to the brain decreased, whether because of fatigue, changes in posture, the completion of digestion, or other factors, the brain's activity was reduced, and sleep resulted. This vascular theory of sleep had genuine observations behind it. The brain does receive a reduced blood supply during certain stages of sleep, compared to wakefulness. Though as it turned out, when the measurements were eventually made more precisely, the relationship is more complex than the simple reduction that the 19th century theorists imagined, and during some stages of sleep, the brain is more rather than less active than during relaxed wakefulness. But the vascular theory was wrong in its causal direction. It was not the reduction in blood flow that caused sleep, but rather whatever caused sleep also caused the reduction in blood flow as part of the broader package of physiological changes that constitute the sleep state. The reduction in blood flow was a correlate of sleep, not its cause. The vascular theory had a competitor in the late 19th century. The chemical theory, which proposed that sleep was caused by the accumulation of specific chemical substances in the blood or the brain during the waking hours. Substances produced by the metabolic activity of the nervous system that had a sleep-inducing effect when they reached sufficient concentrations. The idea had intuitive appeal because it accorded with the common experience that sleep became more pressing as wakefulness continued, as if something were building up that demanded release in sleep. The French physiologist Charles Richet argued in the 1890s that a specific chemical substance, which he called hypnotoxin, from the Greek word for sleep, accumulated in the body during waking and was cleared during sleep. The chemical theory was also essentially correct in its direction, though wrong in its specifics. We now know that several substances, including adenosine, a byproduct of neuronal metabolism, do accumulate during waking and promote sleep, and that caffeine works by blocking the receptors through which adenosine signals the brain that it needs to sleep. But the specific identification of these substances and the mechanisms by which they work would require another century of research and a much more sophisticated understanding of neurochemistry than the 19th century possessed. Neither the vascular theory nor the chemical theory could be definitively tested with the tools available in the 19th century, because neither could be precisely measured. This is the fundamental problem that confronts any scientific investigation of a complex phenomenon. You can hypothesize about mechanisms, but to test your hypotheses you need instruments that can measure what you are hypothesizing about, and the instruments are often the limiting factor. The history of sleep research is, to a significant degree, the history of the development of instruments sensitive enough to measure what was happening in the sleeping brain, and the story of how each new instrument opened new questions even as it answered old ones. The first instrument that made it possible to study the sleeping brain directly, to look at what the brain was actually doing during sleep rather than measuring its indirect effects on blood pressure or body temperature or respiratory rate, was the electroencephalograph, the EEG, and the story of how the EEG came to be invented and how it came to be applied to the study of sleep is a story about a particular human being whose relationship with his own invention was one of the stranger episodes in the history of science. Hans Berger was born in 1873 in Bavaria, the son of a physician, and spent his career as a psychiatrist at the University of Jena. He was, by the accounts of those who knew him, an introverted and socially awkward man, deeply serious, intensely private, more comfortable in his laboratory than in the social and professional worlds of academic medicine. He had one overriding scientific obsession that he pursued for most of his career, the conviction that the brain produced measurable electrical activity that was in some way related to mental processes, and that this electrical activity could be recorded from the surface of the skull. This conviction had a specific origin. As a young man, before he went to medical school, Berger had a terrifying accident. He fell from a horse and nearly went under the wheels of a cannon being towed by the cavalry unit in which he was serving. He was not seriously injured, but on the same evening his sister, who was miles away at their family home, had a sudden premonition of danger and convinced their father to send Berger a telegram inquiring whether he was safe. This experience of apparent telepathy, of mental communication across a physical distance, became for Berger the starting point of a lifelong quest to find the physical basis of mental events, to demonstrate that the thoughts and experiences of one mind could produce measurable physical effects that might be detectable at a distance. The specific scientific program he developed from this starting point was not telepathy research, he was too careful a scientist for that, but rather the attempt to record the electrical activity of the human brain and to correlate those electrical patterns with mental states. If thoughts and mental activity produce changes in the brain's electrical output, those changes should, in principle, be measurable, and the development of electron tube amplifiers in the 1920s gave him, for the first time, the technical means to attempt the measurement. Berger spent nearly 2 decades working in secrecy on the problem, making measurements from patients who had holes in their skulls from neurosurgical procedures or directly from the skull surface of intact subjects. He was so uncertain of his results, so afraid of being wrong or of being ridiculed, that he did not publish them for 5 years after he had convinced himself that he had succeeded. When he finally published, in 1929, his description of what he called the electroencephalogram, the record of the electrical activity of the brain, was greeted with considerable skepticism. The idea that the electrical signals of the brain's billions of neurons, summed across the entire cortex and recorded through the skull, could produce a measurable signal seemed implausible to many of his contemporaries. The British physiologists Edgar Adrian and Brian Matthews confirmed Berger's results in 1934, demonstrating beyond doubt that the EEG was real and measurable, and the field of electroencephalography was born. Adrian, who was already a Nobel laureate for his work on how nerve cells transmitted signals, brought to the validation of Berger's results the authority that Berger himself had lacked. And after Adrian and Matthews's confirmation, the EEG became a topic of serious scientific interest. What the EEG recorded was, in simplified terms, the summed electrical activity of millions of neurons firing in the cortex, detected as tiny voltage changes at the scalp. The raw record, the wavy lines on the paper that the early EEG machines produced, and that modern digital systems still represent in the same basic format, showed patterns that varied with the subject's mental state. When a subject was awake and alert, the EEG showed rapid, irregular waves of relatively low amplitude, a pattern that came to be called beta activity, reflecting the rapid and varied firing of many neurons in different patterns as the brain processed the constant stream of sensory information and cognitive demands of wakefulness. When a subject relaxed with their eyes closed, a slower and more regular pattern appeared, the alpha rhythm, approximately 10 cycles per second, which Berger had identified as one of the fundamental rhythms of the waking brain. And when a subject fell asleep, the EEG changed dramatically. The first systematic study of the EEG during sleep was conducted by the American physiologist Loomis, Harvey, and Hobart in the mid-1930s. They brought subjects into their laboratory, attached electrodes to their scalps, and recorded the continuous electrical activity of their brains through the night. What they found was that the EEG did not simply slow down and flatten when the subject fell asleep, as might have been expected from the vascular theory of sleep as reduced brain activity. Instead, it showed a series of distinct patterns, each characteristic of a different stage of sleep, that cycled through the night in a regular and apparently organized way. They described 5 stages of sleep based on the EEG patterns they observed. In the lightest stage of sleep, the transition from waking, the alpha rhythm that characterized relaxed wakefulness, gradually broke down and was replaced by slower, irregular activity. In deeper stages, the EEG showed increasingly large, slow waves, what would eventually be called delta activity, interspersed with brief bursts of faster oscillation that they called sleep spindles, the characteristic marker of what is now known as stage 2 sleep. In the deepest stage of sleep, the slow delta waves dominated. This was the first time that anyone had directly observed the architecture of sleep, the organized progression through different states that constitutes a night's sleep, and it was a discovery of fundamental importance. Sleep was not a single state, but a series of states, each with its own electrical signature, cycling through the night in a pattern that was apparently consistent across different individuals. The brain was not simply turned off during sleep. It was doing something organized, something structured, something that varied systematically over the course of the night in ways that the waking brain did not. Loomis and his colleagues did not fully appreciate the significance of what they had found, partly because the techniques available to them did not allow them to look at the body as well as the brain during sleep, and partly because the most dramatic discovery still lay ahead of them. They had mapped the architecture of the night, but they had not yet found the room within that architecture that would, when discovered, overturn everything that anyone had thought they understood about what sleep was. The discovery that changed everything was made not by a senior researcher with decades of experience, but by a graduate student who was assigned what seemed at the time to be a fairly routine task. Nathaniel Kleitman was, in the early 1950s, the most experienced sleep researcher in the world, which was not as impressive a distinction as it sounds, since there were almost no sleep researchers in the world in the early 1950s. He was a Ukrainian-born physiologist who had come to the United States in the early 20th century and had spent his career at the University of Chicago studying sleep. His 1939 book, Sleep and Wakefulness, was the comprehensive summary of what was known about the physiology of sleep at that point, a substantial and carefully documented work that covered the behavioral, physiological, and neurological aspects of sleep and wakefulness as they were then understood. Kleitman's laboratory in the early 1950s was a small operation, without the funding or the institutional prestige of the major research groups in physiology and neuroscience. He had a graduate student named Eugene Aserinsky, who was looking for a dissertation project. Kleitman suggested that Aserinsky study the eye movements of sleeping people, a relatively unexplored topic that Kleitman thought might shed some light on the depth and character of different sleep stages. Aserinsky began by studying infants whose eye movements were easy to observe directly, and noticed that infants showed periods of rapid, jerky eye movement during sleep that were quite different from the slow, drifting eye movements of lighter sleep. He moved on to studying adult subjects, using electrodes attached near the eyes to record the electrical signals generated by eye movement, a technique called electrooculography, and found the same phenomenon in adults. Periods during sleep when the eyes moved rapidly beneath the closed lids, in what he described as the same kind of conjugate movements that the eyes make when looking at a moving object in waking life. Aserinsky brought these observations to Kleitman, who was initially skeptical. The eye movement apparatus was known to be technically demanding, and Kleitman was concerned that the rapid eye movements Aserinsky was recording might be artifacts, spurious signals produced by electrode movement or other technical problems rather than real eye movements. He asked Aserinsky to verify his results more carefully, which Aserinsky did, eventually including his own son as a subject, and watching directly through the subject's closed eyelids, to confirm that the rapid eye movements being recorded by the electrodes corresponded to actual physical movement of the eyes. They did. The rapid eye movements were real. And when Kleitman and Aserinsky compared the EEG recordings from the periods of rapid eye movement with the EEG recordings from the rest of the night, they found something that neither of them had expected. The EEG during the rapid eye movement periods looked like the EEG of waking, low amplitude, high frequency, the brain apparently as active as it was during alert wakefulness, embedded within a night otherwise characterized by the slower, higher amplitude patterns of the sleep stages that Loomis had described. Kleitman and Aserinsky published their findings in Science in 1953. The paper was brief, less than 2 pages, and matter-of-fact in its tone, but its implications were enormous. Sleep was not a single state of reduced brain activity. It contained within it periods of intense brain activity, electrically indistinguishable from waking, associated with rapid movements of the eyes. What was happening during these periods, and what did those eye movements mean? The answer to the second question came quickly. When subjects were awakened during periods of rapid eye movement and asked whether they had been dreaming, the vast majority reported vivid, narrative dreams. When subjects were awakened during the other stages of sleep, dream reports were much rarer and typically fragmentary and vague when they did occur. The rapid eye movements and the activated EEG were the physiological signature of dreaming. This was a discovery of extraordinary significance. Dreaming, which humans had been experiencing and wondering about for as long as they had been capable of wonder, the phenomenon that had motivated the dream temples of ancient Egypt, the oneiromancy of the Greeks, the dream interpretation of Freud, had a specific, identifiable, measurable physiological correlate. It happened at particular times during the night, in particular stages of sleep, and it could be detected and studied by external measurement. The subjective experience of dreaming was no longer accessible only from the inside. Kleitman's other graduate student at the time was William Dement, who would go on to become one of the central figures of 20th century sleep research. Dement extended the observations of the 1953 paper, studying the timing and duration of REM periods through the night, and establishing what became known as the sleep architecture. The organized cycling through non-REM and REM stages that characterizes a normal night's sleep. What Dement found was that a night's sleep was not a simple progression from light to deep and back to light again, but a complex cycling between 2 fundamentally different kinds of sleep. The sleep that Loomis had described, the stages characterized by slow waves, sleep spindles, and delta activity, was one kind. The sleep characterized by the activated EEG and rapid eye movements was another kind, something so different from the sleep that surrounded it that it eventually acquired its own name, REM sleep, for rapid eye movement. The non-REM sleep that made up the rest of the night became NREM sleep by contrast. A typical night's sleep, Dement established, began with a period of NREM sleep that deepened progressively through the early stages into the deepest slow-wave sleep, then lightened again, and then transitioned into the first REM period of the night, typically occurring about 90 minutes after sleep onset. This 90-minute REM period was relatively brief, perhaps 10 to 15 minutes. Then the cycle repeated. Another period of NREM sleep, deepening and lightening, followed by another REM period. Over the course of a night, 4 to 6 complete cycles occurred, and the REM periods became progressively longer as the night continued, so that the final REM period before waking might last for 30 to 45 minutes, and the most vivid and most memorable dreaming typically occurred in the early morning hours rather than in the first part of the night. The discovery of REM sleep transformed sleep research from a peripheral curiosity into a central topic of neuroscience, the question of what REM sleep was for, why the brain should enter this strange state of intense electrical activity accompanying vivid dreaming, with a specific pattern of muscle paralysis that prevented the dreaming body from acting out the dream, became one of the central questions of brain science in the second half of the 20th century, and it remains incompletely answered today. But before following that question into the decades of research it generated, it is worth pausing to appreciate how radical the discovery was in its original context. The standard view of sleep before 1953 was that it was a state of reduced brain activity, a partial dormancy, a daily retreat into something resembling the torpor of hibernation, during which the brain rested and the body recovered. This view was not merely a popular misconception, it was the consensus of the scientific literature, consistent with everything that had been measured and observed. The vascular theory and the chemical theory both assumed that sleep involved a reduction in brain function. The EEG findings of Loomis and his colleagues had complicated this picture by showing that the sleeping brain was not uniformly quiet, but had organized stages, but the overall picture was still of a brain that was less active during sleep than during waking. The discovery of REM sleep demolished this picture entirely. During REM sleep, the brain was not less active than during waking. It was equally active, or in some respects more active, showing the same electrical patterns as alert, engaged wakefulness. The sleeping brain was not dormant. It was busy, doing something that used as much neural processing power as conscious engagement with the waking world, something whose nature and purpose were completely unknown. The years between the discovery of REM sleep in 1953 and the end of the 20th century were years of accelerating discovery in sleep science, as the new field attracted researchers, funding, and institutional support, and as new techniques, beyond the EEG, new methods for measuring brain activity and body chemistry during sleep, opened new windows into what the sleeping brain was doing and why. One of the most important lines of investigation in the years following the REM discovery concerned the neurological basis of sleep itself. The question of which brain structures were responsible for generating and maintaining the different sleep states. The answer, when it came, was surprising in its specificity. Sleep was not simply the passive result of the brain's activity winding down at the end of the day, but was actively generated by specific brain structures that had the function of putting the brain to sleep and keeping it there. The investigation of this question was accelerated by a series of dramatic clinical observations that had been accumulating since the early 20th century, observations that pointed to specific brain regions as critical for the regulation of sleep and wakefulness. The most important of these came from an epidemic that swept Europe and North America in the years immediately following the First World War. Between 1915 and 1926, a mysterious disease called encephalitis lethargica, sleeping sickness, as it was popularly known, though it had nothing to do with the African sleeping sickness caused by the trypanosome parasite, struck approximately 5 million people worldwide, killing perhaps 1 million of them, and leaving many of the survivors with lasting neurological damage. The disease was characterized by severe disruption of sleep and wakefulness. Some patients slept almost continuously, unable to be roused. Others were unable to sleep at all. Still others showed inversions of the normal sleep-wake cycle, sleeping all day and lying awake through the night, and some oscillated between extremes of sleepiness and agitation. The neurologist Konstantin von Economo, who studied the disease systematically during the epidemic and described it in detail, performed post-mortem examinations on patients who had died, and found that the pattern of neurological damage showed a striking correlation with the specific sleep disorder the patient had exhibited. Patients who had been excessively sleepy had damage concentrated in a region at the top of the brainstem and the front of the hypothalamus, a region that von Economo identified as containing structures that were necessary for wakefulness. Patients who had been unable to sleep had damage in a different region, at the back of the hypothalamus, that appeared to contain structures necessary for sleep. Von Economo's observations, made without modern neuroimaging, without modern neurochemistry, relying only on careful clinical observation and post-mortem anatomy, identified the hypothalamus as a central regulatory region for sleep and wakefulness, a conclusion that subsequent decades of research would confirm and elaborate in extraordinary detail. The hypothalamus, a small region at the base of the brain about the size of an almond, contains within it the neural circuits that control the transition between sleeping and waking. Circuits that are still the subject of intense research and that have become the target of most of the sleep medications developed in the late 20th and early 21st centuries. The Swiss researcher Walter Rudolf Hess demonstrated in the 1920s and 1930s that electrical stimulation of specific hypothalamic regions in cats could reliably produce sleep, that the act of delivering a small electrical current to the right spot in the hypothalamus would cause an awake cat to lie down, close its eyes, and fall asleep within seconds. This was one of the most dramatic demonstrations in the history of brain research. Sleep was not something that happened passively when the brain ran out of energy, but something that was actively induced by a specific brain circuit that could be turned on by a switch. Hess received the Nobel Prize in Physiology or Medicine in 1949 for this work. The American researcher Horace Magoon and his colleague Giuseppe Maruzzi made a complementary discovery in 1949. They identified a region in the brainstem called the reticular activating system and showed that stimulation of this region produced immediate waking in sleeping animals. The reticular activating system was a diffuse network of neurons that sent activating signals throughout the cortex, and its activity was necessary for maintaining wakefulness. When it was active, the cortex was alert and responsive. When it was suppressed, sleep ensued. This made the reticular activating system the neurological basis of what von Economo had identified clinically: the wakefulness-promoting circuit, whose destruction in encephalitis lethargica produced the devastating sleepiness he had observed. Together, these discoveries established a basic framework for the neural regulation of sleep and wakefulness. The brain contained both sleep-promoting and wake-promoting circuits, and the sleep-wake cycle was the result of their interaction, a constant competition between the circuits that drove wakefulness and those that drove sleep, with the outcome at any given moment determined by which system had the upper hand. This framework, now known as the flip-flop model of sleep-wake regulation, remains the foundation of current understanding, though it has been enormously elaborated and refined by subsequent research. The specific neurotransmitters involved in this competition were identified over the following decades as the tools of neurochemistry became available to sleep researchers. The wake-promoting side of the competition turned out to involve several different neurotransmitter systems: norepinephrine, released by neurons of the locus coeruleus; serotonin, released by neurons of the raphe nuclei; histamine, released by neurons of the tuberomammillary nucleus; and acetylcholine, released by neurons in the basal forebrain and brainstem. All of these systems were active during waking, and their activity promoted and maintained the state of alert consciousness. During sleep, their activity decreased dramatically. The sleep-promoting side of the competition was initially less well understood. The hypothalamic neurons that von Economo had identified as necessary for sleep were found to release a neurotransmitter called GABA, the main inhibitory neurotransmitter of the brain, and to use it to suppress the activity of the wake-promoting systems. When the GABA-releasing sleep neurons were active, they inhibited the wake-promoting neurons, reducing their output and allowing the brain to transition into sleep. The understanding of this GABAergic sleep switch had immediate practical implications because it explained how a class of drugs that had been in clinical use for decades, the barbiturates and later the benzodiazepines, actually worked. Both classes of drugs enhanced the activity of GABA in the brain, and both produced sedation and sleep as a result. The mechanism was now understood, even if the original development of these drugs had been entirely empirical. The barbiturates were synthesized in the early 20th century and found to produce sleep without any understanding of how they did so, simply because they worked. Understanding why they worked opened the possibility of developing better, more targeted drugs, and the sleep pharmacology of the late 20th century was in large part the story of the search for drugs that could act more selectively on the specific sleep-promoting circuits without the side effects, the hangover, the impaired cognition, the risk of dependence, that the broad GABA enhancement of the barbiturates and benzodiazepines produced. While the neurological basis of sleep was being worked out, another line of investigation was addressing a different but equally fundamental question. What was sleep actually doing? The mechanisms that generated and maintained sleep were becoming clearer, but the function of sleep, the reason why the brain should devote a third of its life to this state, the reason why its absence should be so rapidly and so dramatically harmful, remained obscure. The most obvious hypothesis about sleep's function was that it served restoration, that sleep was the period during which the body and brain recovered from the wear and tear of the waking day, repaired damaged tissues, cleared metabolic waste, and restored the physiological systems that waking activity depleted. This restorative theory of sleep had ancient roots, going back to Aristotle's account of sleep as the period when digestive processes could complete undisturbed, and it had obvious intuitive support in the experience of anyone who has ever felt tired, and then, after a night's sleep, felt better. The restorative theory received significant scientific support from research on growth hormone, one of the hormones released in regular pulses by the pituitary gland, which was found to be released almost exclusively during the first few hours of sleep, specifically during the periods of deepest slow-wave sleep. Growth hormone promotes tissue repair and protein synthesis, and its selective release during sleep suggested that the early part of the night was a period of intensive physical restoration, using the hormone to drive the repair and growth of tissues throughout the body. The observation that children, who are growing rapidly, showed more slow-wave sleep and higher growth hormone release than adults, and that athletes showed increased slow-wave sleep after intensive training, supported the idea that slow-wave sleep was specifically a restorative state. The restorative theory also received support from studies of sleep deprivation, which produced a remarkably consistent pattern of physiological and cognitive deterioration. After one night without sleep, subjects showed elevated levels of inflammatory markers in the blood, reduced immune function, impaired glucose metabolism, and significant deterioration in attention, memory, and judgment. After several consecutive nights of sleep deprivation, the deterioration became more severe, eventually producing hallucinations, cognitive disintegration, and, in the extreme cases of experimental sleep deprivation in animals, death. The sleep deprivation research of the 20th century produced some of its most dramatic and disturbing findings in animal studies, particularly in the experiments conducted by the University of Chicago researcher Alan Rechtschaffen in the 1980s and 1990s. Rechtschaffen developed a technique for keeping rats continuously awake by placing them on a turntable over water. Whenever the rat's EEG showed the pattern of sleep onset, the turntable rotated, forcing the rat to walk or fall into the water. Using this technique, Rechtschaffen could keep rats awake indefinitely, or nearly so, since no rat survived the experiment for more than 5 to 6 weeks. The rats deprived of all sleep showed a progression of pathological changes. They developed sores on their skin that would not heal. Their fur became unkempt and then began to fall out. They lost weight, despite eating more than normal. Their core body temperature dropped despite generating more metabolic heat. And they eventually died in a state that resembled the deterioration of a severely immunocompromised patient. The cause of death was never clearly identified. The damage was too widespread to be attributed to a single organ failure. But the experiment demonstrated beyond any doubt that sleep was not merely pleasant or convenient, but was biologically necessary in a fundamental sense. The question of why rats deprived of sleep died from the damage they showed, and why the damage appeared to be specifically connected to the absence of sleep rather than to the stress of the deprivation procedure, became one of the driving questions of sleep research in the 1990s. One of the answers that emerged pointed toward a function of sleep that had not previously been recognized: the clearance of metabolic waste from the brain. The discovery in question was made in the 2000s when the neurologist Micah Nedergaard and her colleagues at the University of Rochester identified what they called the glymphatic system, a network of channels surrounding the brain's blood vessels that serve to flush cerebrospinal fluid through the brain tissue, carrying with it the molecular byproducts of neural activity. During waking, this glymphatic system was relatively inactive. During sleep, specifically during the slow-wave sleep of the early night, it became dramatically more active, with the channels expanding and the flow of cerebrospinal fluid increasing, efficiently clearing the metabolic waste that had accumulated during the day. Among the waste products that the glymphatic system cleared was amyloid beta, a protein fragment that, when it accumulates, forms the plaques that are the hallmark of Alzheimer's disease. The discovery that slow-wave sleep was specifically associated with the clearance of amyloid beta from the brain provided a potential mechanistic link between sleep disruption and Alzheimer's disease, a link that subsequent epidemiological research found support for in the observation that chronic poor sleep in middle age was associated with elevated risk of Alzheimer's decades later. The glymphatic discovery was greeted with great excitement because it provided a compelling and mechanistically specific answer to one of the oldest questions in sleep research. Why does the brain need to sleep specifically rather than simply resting quietly while the body recovered? The brain, it now appeared, needed sleep not just for general restoration but for a specific maintenance function that it could not perform while it was awake, the clearing of the toxic byproducts of its own activity. The sleeping brain was not simply resting, it was cleaning itself, performing a maintenance function that was as necessary for its long-term health as any other aspect of its biology. While the restoration and maintenance functions of sleep were being elucidated, another line of research was investigating a function of sleep that turned out to be equally fundamental, its role in memory and learning. The relationship between sleep and memory had been observed informally for centuries. Students had long noted that reviewing material before sleep seemed to improve retention, and the phrase, "let me sleep on it," embedded in common speech, reflected a widespread intuition that difficult problems seemed clearer after sleep. But the scientific investigation of this relationship did not begin seriously until the 20th century. The early studies, conducted in the 1920s and 1930s, established the basic phenomenon. Information learned before sleep was better retained than information learned at an equivalent interval during waking activity. John Jenkins and Carl Dallenbach published a study in 1924 in which they had subjects memorize lists of nonsense syllables, then either slept or remained awake for intervals of various lengths before being tested for retention. The subjects who slept retained significantly more of what they had learned, and the retention advantage of sleep increased with the length of the sleep period. Jenkins and Dallenbach interpreted their result as showing that sleep protected memories from interference, that during waking new experiences continuously disrupted and overwrote earlier memories, while during sleep, in the absence of new experiences, memories were protected from this interference. This interference theory of sleep's benefit for memory was a reasonable interpretation of the available data, and it had some truth to it. The absence of new interfering information during sleep does protect memories from overwriting. But subsequent research revealed that sleep was not merely passively protecting memories from interference, but was actively processing them, consolidating, organizing, strengthening, and integrating them with existing knowledge in ways that transformed their neural representation. The discovery of REM sleep gave memory researchers a new handle on the problem, because it provided a physiologically distinct stage of sleep that could be selectively manipulated. If REM sleep was important for memory, then selectively preventing it should impair memory consolidation. The first experiments to test this prediction, conducted in the 1960s and 1970s, produced mixed results. Some studies found that REM deprivation impaired memory, others did not, and the interpretation was complicated by the difficulty of selectively depriving subjects of REM sleep without disturbing their sleep generally, and by the rebound of REM sleep that occurred when the deprivation ended. The resolution of these difficulties, and the establishment of a clear and detailed picture of how sleep processed memories, required the new neuroscience of the late 20th century. The ability to record the activity of individual neurons in sleeping animals, and eventually the ability to image the human brain during sleep using PET scanning and later fMRI. When these tools were brought to bear on the sleep-memory relationship, they revealed a picture of extraordinary complexity and sophistication. The consolidation of memories during sleep turned out to involve not one, but two distinct processes, occurring during two different stages of sleep. The slow-wave sleep of the early night was responsible for the consolidation of declarative memories, the explicit, consciously accessible memories of facts and events that form the narrative of personal and factual knowledge. During slow-wave sleep, the hippocampus, the brain structure most critical for forming new memories, repeatedly reactivated the patterns of neural activity that had been established during learning, and these reactivations were coordinated with the large, slow oscillations of the EEG, the sleep spindles and the slow waves, in a way that transferred the memory traces from the hippocampus to the neocortex, where they could be stored long-term without continuing to require the hippocampus. The REM sleep of the later part of the night was responsible for a different kind of memory processing, the integration of new information with existing knowledge, the extraction of abstract patterns and rules from specific experiences, and the processing of emotional memories in a way that reduced their emotional intensity while preserving their informational content. The specific neurochemical environment of REM sleep, characterized by high levels of acetylcholine and low levels of the norepinephrine and serotonin that dominate during waking, appeared to create conditions uniquely suited for this integrative processing, allowing the brain to make connections between new experiences and existing knowledge that the more focused, norepinephrine-driven waking brain was less likely to make. The role of REM sleep in emotional memory processing was one of the most practically significant findings of late 20th century sleep research, because it provided a potential mechanism for a clinical observation that had been made repeatedly, that people who were deprived of REM sleep, or who had conditions that reduced REM sleep, showed heightened emotional reactivity and difficulty regulating their emotional responses. The psychiatrist Matthew Walker, whose research at UC Berkeley became some of the most widely read sleep science writing of the early 21st century, proposed a theory of REM sleep as a kind of overnight therapy. During REM sleep, the brain processed the emotional memories of the day in a neurochemical environment that allowed the memory to be retained while reducing its emotional charge, essentially stripping the distress from the memory while keeping the information. Without adequate REM sleep, emotional memories retained their raw, unprocessed quality, contributing to the rumination and emotional dysregulation that characterized anxiety disorders and depression. This theory had immediate implications for the treatment of trauma. Post-traumatic stress disorder, in Walker's account, could be understood partly as a failure of the REM sleep mechanism that normally processed and diffused the emotional content of traumatic memories, a failure that left those memories in their original raw, intrusive form, continuing to generate the full emotional response of the original trauma each time they were activated. Research on sleep in PTSD patients found that they showed distinctive abnormalities in REM sleep architecture, including more frequent awakenings from REM sleep, as if the processing mechanism was being overwhelmed, and distinctive EEG patterns during REM that differed from those of healthy subjects. The work on sleep and memory also produced one of the most dramatic individual findings in the history of sleep research: the discovery that sleep was specifically associated with creative insight. In a study published in 2004, the German researcher Ulrich Wagner had subjects work on a mathematical puzzle that could be solved by a laborious method, or by a much faster method that required recognizing an underlying pattern that was not immediately apparent. After a training session, subjects were either allowed to sleep or kept awake for an equivalent period, then retested. The subjects who had slept were nearly 3 times as likely to have discovered the shortcut method as those who had remained awake, a dramatic demonstration that sleep was specifically facilitating the kind of insight that involves recognizing non-obvious patterns. This finding gave scientific support to one of the most widely reported experiences in the history of creative and scientific work: the phenomenon of waking up with the solution to a problem that had been intractable the evening before, or of the problem seeming clearer and more tractable after sleep than it had seemed the night before. The German chemist August Kekulé famously reported that the ring structure of benzene came to him in a dream of a snake biting its own tail. The mathematician Henri Poincaré described the solution to a mathematical problem that had resisted his waking efforts coming to him at the moment of waking from sleep. Countless other scientists, artists, and thinkers have reported similar experiences. The sleep insight research provided a mechanistic basis for these anecdotes. REM sleep, in particular, appeared to facilitate the kind of loose associative thinking that makes non-obvious connections between ideas, and this facilitation of associative thinking was the neural basis of what experienced as insight or inspiration. By the end of the 20th century, sleep science had transformed from the marginal curiosity of Kohlschutter's era into one of the most active and practically consequential areas of biomedical research. The EEG had been supplemented by neuroimaging, by molecular genetics, by pharmacology, by clinical epidemiology. A whole battery of tools that had revealed the extraordinary complexity of what happened in the brain during those 8 hours of unconsciousness that the 19th century had assumed to be simply the brain at rest. The brain was not at rest. It was cycling through states of deep slow-wave restoration and REM dreaming, clearing its toxic waste products, consolidating the day's memories, processing its emotional experiences, and making creative connections between ideas that the focused, goal-directed waking mind was too busy to make. It was maintaining the calibration of the immune system, regulating the release of hormones that controlled growth and metabolism, and preserving the delicate balance of neurotransmitters on which mood and cognition depended. It was, in short, doing the work of being a brain, the maintenance work, the processing work, the organizational work, during the hours that had previously been assumed to be empty. The person lying still in their bed, breathing slowly, with their eyes closed and their voluntary muscles paralyzed by the neural circuits that prevented them from acting out their dreams, was not doing nothing. They were not even doing something simple. They were engaged in one of the most complex and consequential activities that biological systems are capable of, an activity so complex that decades of intensive research had produced a detailed account of its mechanisms without yet producing a complete account of its purpose. The purpose remained, in the most fundamental sense, uncertain. The accumulation of evidence for sleep's functions, restoration, waste clearance, memory consolidation, emotional processing, immune maintenance, metabolic regulation, was impressive, but it was not a complete explanation. Each of these functions could be pointed to and measured, but none of them individually, or even all of them together, entirely explained why sleep evolved as the solution to the body's and brain's maintenance needs. Why was the brain unable to perform these functions during waking? Why was the muscle paralysis of REM sleep necessary? Why did dreaming take the specific form it did? The narratives, the characters, the emotions, the apparent meaningfulness of content that seemed to follow its own internal logic while making no reference to the constraints of the physical world. These questions would be the inheritance of the 21st century. And the 21st century, with its new tools and its new frameworks, would push the understanding further, discovering things about the sleeping brain that the researchers of Kleitman and Aserinsky's generation could not have imagined, and raising new questions that their successors would need to answer. But that is where we are going. For now, in the last decades of the 20th century, the field of sleep science stood at a point of remarkable achievement and genuine uncertainty, having discovered more about the sleeping brain in 50 years than had been discovered in the previous 5,000, and still unable to give a fully satisfying answer to the question that every person who has ever wondered at the experience of waking from sleep has implicitly asked. What really happens when you fall asleep? The answer, it was becoming clear, was something far more extraordinary than anyone had imagined. What really happens when you fall asleep? The answer, it was becoming clear, was something far more extraordinary than anyone had imagined. The 21st century arrived in sleep science with a set of tools that would have seemed fantastical to the researchers who had mapped the basic architecture of the sleep cycle in the 1950s and 1960s, where Aserinsky and Kleitman had recorded the sleeping brain through the blunt instrument of the EEG, measuring the summed electrical activity of millions of neurons from electrodes pasted to the scalp, producing a signal that was informative but limited, like trying to understand a symphony by listening to it through a wall. Their successors now had functional magnetic resonance imaging, which could track blood flow changes in specific millimeter-scale regions of the brain with a temporal resolution of seconds. They had positron emission tomography, which could trace the activity of specific neurotransmitter systems by following radioactively labeled molecules as they move through the brain. They had optogenetics, which allowed researchers to turn specific populations of neurons on and off with pulses of light, dissecting the neural circuits of sleep and wakefulness with a precision that was impossible with any previous technique. They had the tools of molecular genetics, which allowed them to identify the genes involved in sleep regulation, to create animals in which those genes were modified, and to watch how the modifications changed the animal's sleep. And they had a vast accumulation of epidemiological data, studies of hundreds of thousands of people that track the relationship between their reported sleep patterns and their subsequent health outcomes over periods of years and decades, that had transformed sleep from a laboratory curiosity into a public health concern of the first magnitude. The epidemiological findings were, in many respects, the most immediately impactful discoveries of the early 21st century in sleep research, because they connected the laboratory science to the lives of ordinary people in ways that were impossible to ignore. Study after study, from research groups around the world using different methodologies and different populations, arrived at the same general finding, that people who slept less than 7 hours a night showed significantly elevated risk for a remarkably broad range of serious health conditions. Not slightly elevated risk. Significantly, sometimes dramatically elevated risk, with the relationship between sleep duration and health outcomes showing a consistency across different diseases and different populations that was difficult to attribute to confounding factors. The conditions associated with chronic short sleep included cardiovascular disease. People who regularly slept fewer than 6 hours a night showed approximately twice the risk of heart attack and stroke compared to those who slept 7 to 8 hours. They included type 2 diabetes. Short sleep was associated with impaired glucose metabolism and insulin resistance, the precursors of diabetes, through mechanisms that turned out to involve specific hormonal changes that occurred during sleep. They included obesity. Sleep deprivation disrupted the hormonal regulation of appetite, reducing levels of the satiety hormone leptin and increasing levels of the hunger hormone ghrelin, producing an increase in appetite and a preference for high-calorie foods that persisted across days of restricted sleep. They included cancer. Several large epidemiological studies found elevated cancer risk in individuals with chronic sleep disruption, with the relationship strongest for colorectal cancer, breast cancer, and prostate cancer, possibly through the disruption of immune surveillance that occurred with sleep deprivation. They included Alzheimer's disease, as the glymphatic research had suggested. They included depression and anxiety disorders. They included infectious disease susceptibility, a controlled study in which volunteers were deliberately exposed to rhinovirus, the virus responsible for the common cold, found that subjects who had been sleeping fewer than 6 hours a night in the preceding weeks were 4 times more likely to develop a cold than those who had been sleeping 7 or more hours. The breadth of this health impact, the fact that sleep duration was associated with risk for so many different serious conditions, was both the most striking aspect of the epidemiological findings and the most theoretically informative. If sleep disruption increased risk for cardiovascular disease but not for cancer, or for metabolic disorders but not for infectious disease, it would suggest that sleep had specific, limited functions whose disruption affected specific health domains. The fact that its disruption appeared to increase risk across a wide range of conditions suggested that sleep was doing something fundamental, maintaining some basic aspect of biological functioning that was relevant to health generally, not just to specific diseases. This inference was consistent with what the laboratory science was revealing, that sleep was not a collection of specific functions, each of which could be turned off independently, but was a state of the organism that served as the foundation for biological functioning generally. The various specific functions that had been identified, the glymphatic clearance, the memory consolidation, the immune calibration, the hormonal regulation, were not independent processes that happened to require sleep. They were aspects of a single, integrated biological state whose requirement for sleep reflected the deep organization of the biological systems that performed them. The deepest question in sleep science, the question that the epidemiological findings made more urgent and that the laboratory science was addressing with new tools, was the evolutionary question. Why had sleep evolved? What selective pressures had shaped an organism that needed to spend a third of its life in a state of reduced responsiveness to the environment, a state that made it vulnerable to predation, that prevented it from foraging or reproducing, or performing any of the other activities through which organisms accumulated fitness? The evolutionary cost of sleep was real and large. What benefit was large enough to justify that cost? The question was not new. It had been asked in various forms since Darwin, and the absence of a satisfying answer had been a persistent embarrassment for sleep science. The catalogue of sleep's functions, restoration, waste clearance, memory consolidation, emotional processing, provided potential answers, but each had problems when examined closely. Restoration, for example, surely the body could restore itself during quiet wakefulness, as it does during the periods of rest that do not involve sleep. Why was the specific state of sleep, unconsciousness, muscle paralysis, reduced responsiveness, necessary for restoration that seems like it could happen just as well with the brain awake? The glymphatic clearance was a more compelling answer, because the dilation of the glymphatic channels that occurred during sleep appeared to require the specific neural state of sleep rather than just quiet rest. But it was still not clear why the brain could not clear its waste during waking if it needed to, or why the evolution of the glymphatic system should have required sleep rather than waking clearance. The memory consolidation argument was perhaps the most compelling evolutionary answer, because it pointed to a function that was specifically cognitive, that enhanced the brain's ability to learn and adapt, and that therefore conferred a fitness advantage that was easy to quantify in principle, even if difficult in practice. An organism that slept and consolidated its memories and learned better would outcompete an organism that did not sleep and did not consolidate, regardless of the vulnerability that sleep imposed. The survival advantage of superior learning might be large enough to outweigh the vulnerability cost of sleep. But this argument also had difficulties. Memory consolidation, the research showed, required specifically slow-wave sleep and REM sleep, not just any reduction in activity. And the specific duration and architecture of sleep, the particular cycle length, the particular proportions of slow-wave and REM sleep, varied across species in ways that were not obviously predicted by their learning needs. Dolphins and porpoises, which are highly intelligent animals with complex social lives and presumably substantial learning needs, show a pattern called unihemispheric sleep, in which only one hemisphere of the brain sleeps at a time, while the other remains awake, a pattern that seems to serve the function of maintaining environmental awareness while still obtaining some of the benefits of sleep, but whose relationship to memory consolidation is unclear. The unihemispheric sleep of cetaceans was one of the most fascinating findings in the comparative biology of sleep, and it had implications that extended beyond the interesting question of how dolphins navigated the competing demands of sleep and environmental vigilance. It suggested that the specific form of sleep, the bilateral loss of consciousness, the muscle paralysis, the complete withdrawal from the environment, was not the only possible solution to whatever problem sleep solved, but was one of several possible solutions that evolution had arrived at in different lineages. This implied that the problem sleep solved was real and important enough that evolution had found multiple different ways to solve it, but that the specific solution depended on the ecological pressures and the neural architecture of the particular organism. The ecological pressures on sleep were illuminated by a body of comparative research that examined the relationship between an animal's sleep duration and its ecological situation, its diet, its predator pressure, its body size, its social structure. The general finding was that animals high on the food chain, predators who did not need to worry much about being eaten while they slept more than animals low on the food chain, prey species, who faced significant risks from sleep's vulnerability. Lions and tigers, who had no natural predators and ate relatively infrequently, slept 15 to 20 hours a day. Horses and cows, who were prey animals and needed to maintain continuous vigilance, slept only 2 to 4 hours a day and could sleep standing up. Elephants, who were large and socially protected by their herds, slept 4 to 6 hours a night in 2-hour blocks. Humans, within this comparative framework, were anomalous. Human hunter-gatherer societies, studied by researchers including Jerome Siegel, who spent years collecting sleep data from traditional societies in Africa and South America that were not exposed to artificial light and modern work schedules, showed sleep patterns quite different from the 7 to 9 hours that contemporary sleep recommendations specified. The Hadza of Tanzania, the San of Namibia, and the Tsimane of Bolivia all showed average sleep durations of 6 to 7 hours, with consistent patterns of going to sleep about 3 hours after sunset and waking before or around sunrise. They did not nap during the day. Their sleep was consolidated into a single period, not segmented in the way that Kirch's historical research had suggested for pre-industrial Europeans. Siegel's research was controversial, partly because it challenged the widely propagated narrative that modern people were chronically sleep-deprived compared to their ancestors, and partly because it raised questions about the basis for the widely repeated recommendation of 8 hours of sleep as the universal human requirement. If traditional societies whose members were not exposed to artificial light or caffeine slept 6 to 7 hours and appeared to be healthy, was 8 hours really the appropriate target? Or were there aspects of contemporary sleep that differed from traditional sleep in ways that affected its restorative quality, perhaps not just its quantity? The controversy over optimal sleep duration was a microcosm of a broader tension in sleep science between the population-level findings of epidemiology, which suggested that short sleep was associated with worse health outcomes, and the individual variation in sleep need, which made it difficult to specify a single optimal sleep duration that applied to everyone. Some people, controlled laboratory experiments had established, were genuinely short sleepers, people who felt well and performed normally on a fraction of the sleep that most people required, and who showed no physiological markers of sleep deprivation. These individuals, who constituted perhaps 3 to 5% of the population, appeared to have a genetic basis for their reduced sleep need. Studies of families in which short sleep was inherited identified mutations in specific genes, including the gene for the DEC2 protein, that appeared to increase the efficiency of sleep in a way that allowed the biological work of a full night to be accomplished in fewer hours. The genetics of sleep need was one of the most active areas of early 21st century sleep research, and it had implications that went beyond the question of individual variation in sleep duration. The identification of specific genes that affected sleep need, and the larger number of common genetic variants that influenced sleep timing, sleep architecture, and susceptibility to sleep disorders, pointed toward a future in which the assessment and treatment of sleep problems would be personalized in the same way that cancer treatment was being personalized, based on the specific genetic profile of the individual rather than on population averages. The sleep disorders that affected a substantial fraction of the population, insomnia, sleep apnea, narcolepsy, restless leg syndrome, and various others, were transformed by the new biology of sleep in ways that had direct clinical consequences. Insomnia, the most common sleep disorder, affecting perhaps 30% of the adult population to some degree, and 15% severely enough to cause significant daytime dysfunction, had been treated with increasing pharmacological sophistication through the 20th century. From the barbiturates of the early 20th century to the benzodiazepines of the mid-century to the Z drugs, zolpidem, zopiclone, esopicolone of the late 20th century. Each generation of drugs had been an improvement on the previous in some respects. The Z drugs had a shorter duration of action and fewer next-day effects than the benzodiazepines, and fewer risks of dependence than the barbiturates, but all of them worked by the same general mechanism, enhancing GABA activity to suppress the arousal systems and allow sleep to begin. The pharmacological approach to insomnia was challenged in the early 21st century by the accumulating evidence that cognitive behavioral therapy for insomnia, a structured psychological treatment that addressed the thoughts and behaviors that perpetuated the condition rather than simply suppressing arousal with drugs, was more effective than medication in the long term, producing durable improvements in sleep that persisted after treatment ended rather than being dependent on continued drug use. This finding was not entirely surprising to those who understood the neuroscience of insomnia, because the condition turned out to involve not just a failure of the sleep-promoting systems, but an excessive activation of the arousal systems, a state of hyperarousal in which the brain was too alert, too vigilant, too unable to reduce its own activity to allow sleep to begin. The hyperarousal of insomnia showed specific signatures in brain imaging. Insomniacs showed elevated metabolic activity in the regions associated with emotional processing and self-referential thought, the same regions that were active when people were ruminating, worrying, reviewing the events of the day, compared to people who slept normally. The insomnia brain was not a brain that couldn't get tired enough to sleep. It was a brain that couldn't get calm enough. The rumination that insomniacs reported, the inability to stop thinking, the circular review of worries and concerns that characterize the experience of lying awake, had a specific neural correlate, and it was the identification of this correlate that explained why cognitive behavioral therapy, which specifically targeted and modified the patterns of thought that drove the hyperarousal, was more effective in addressing the underlying problem than drugs that simply suppressed the arousal pharmacologically. Sleep apnea, the condition in which breathing repeatedly stops during sleep, triggering brief arousals that fragmented sleep without the person's awareness, had been recognized as a clinical entity since the 1970s and treated with continuous positive airway pressure, CPAP, since the 1980s, but its full epidemiological impact was not appreciated until large-scale studies in the 1990s and 2000s established that it was far more common than previously thought, affecting perhaps 15 to 30% of middle-aged men and up to 5% of middle-aged women, and that its health consequences were severe: dramatically elevated risk of cardiovascular disease, metabolic disease, and cognitive decline, as well as the substantial daytime functional impairment that resulted from repeatedly fragmented sleep. The mechanism connecting sleep apnea to cardiovascular disease involved several pathways: the repeated episodes of oxygen desaturation that accompanied the breathing pauses, the sympathetic nervous system activation triggered by each arousal, and the inflammatory response that chronic intermittent hypoxia induced. Narcolepsy, the sleep disorder characterized by excessive daytime sleepiness, sudden loss of muscle tone triggered by strong emotions, cataplexy, and the intrusion of REM-like phenomena into waking, had been one of the most mysterious sleep disorders until a series of discoveries in the late 1990s identified its cause with a precision that had no parallel in psychiatry or neurology. In 1999, two groups of researchers, one working with dogs that had a hereditary form of narcolepsy, the other studying knockout mice, in which a specific gene had been inactivated, identified the neuropeptide hypocretin, also called orexin, as the key molecule in the regulation of wakefulness, and established that narcolepsy resulted from the loss of the hypocretin-producing neurons in the hypothalamus. The story of the hypocretin discovery was one of the great detective stories of modern neuroscience. The dog narcolepsy had been studied for years by William Dement, the same William Dement who had helped establish the basic architecture of the sleep cycle in the 1950s, and who had gone on to found the first dedicated sleep clinic at Stanford in 1970. Dement's narcoleptic dogs would be walking normally, and then, at a moment of excitement, the anticipation of food, the greeting of a familiar person, would suddenly collapse, their muscles giving way completely, falling to the floor in what looked like sleep, but from which they recovered within a minute or two. The similarity to human cataplexy was obvious, and the dogs had served as a model for studying the genetic basis of the condition for decades. The discovery that the human form of narcolepsy with cataplexy resulted specifically from the loss of hypocretin neurons that in healthy brains sent activating signals to the wake-promoting systems throughout the brain, maintaining the stability of wakefulness against the competing pull of sleep, provided not only an understanding of narcolepsy, but a broader insight into the flip-flop model of sleep-wake regulation. Hypocretin was the stabilizer of the flip-flop switch. Without it, the switch between sleep and waking became unstable, flipping inappropriately and involuntarily in both directions. The daytime sleepiness and sleep attacks of narcolepsy representing inappropriate flips into sleep, and the cataplexy representing the inappropriate intrusion of the muscle atonia of REM sleep into waking consciousness. The autoimmune nature of the hypocretin neuron loss, the finding that in most cases of human narcolepsy, the immune system had specifically targeted and destroyed the hypocretin neurons, connected narcolepsy to the broader field of autoimmune disease and opened the possibility of eventual preventive treatment. More immediately, it established hypocretin as a potential pharmacological target, and the development of orexin receptor antagonists, drugs that blocked the hypocretin receptors and thereby promoted sleep by reducing the stabilizing effect of hypocretin on wakefulness, became one of the major directions of sleep pharmacology in the early 21st century. Suvorexant, approved by the FDA in 2014, was the first drug in this class to reach clinical use, representing the first fundamentally new mechanism for sleep-promoting medication since the discovery of the GABA connection decades earlier. The most dramatic and most publicly discussed development in sleep science in the early 21st century was not a discovery in the laboratory, but a crisis in society. The epidemiological evidence that had accumulated in the first 2 decades of the century, the clinical research on the health consequences of sleep disorders, the neuroscience of sleep's functions, all of this pointed toward a single, deeply uncomfortable conclusion that the modern world, in the richest and most technologically sophisticated societies in human history, had created conditions in which a substantial fraction of the population was chronically, severely sleep-deprived, and that this deprivation was exacting a health toll of extraordinary magnitude. The evidence for widespread sleep deprivation was consistent across multiple sources. Self-reported sleep duration in the United States had declined significantly over the 20th century. Americans in the 1910s and 1920s had reported average sleep durations of around 9 hours, compared to the 6.5 to 7 hours reported in surveys from the 2000s and 2010s. National Health Interview survey data showed that the fraction of American adults reporting 6 or fewer hours of sleep per night had increased from 12% in 1985 to 38% by 2012. Similar trends were observed in the United Kingdom, Japan, South Korea, and other industrialized countries, with the most dramatic declines seen in the societies that had most thoroughly adopted the 24-hour economy, the expectation that productive activity should be available and appropriate at all hours. The drivers of this decline were multiple and interacting. The most important was probably the spread of artificial light, particularly in its most recent and most effective form. The screens of electronic devices that produced light in the blue spectrum wavelengths to which the circadian system was most sensitive. The circadian clock, the biological timing system, located in a tiny region of the hypothalamus called the suprachiasmatic nucleus that coordinated the timing of the body's physiological processes with the 24-hour cycle of the Earth's rotation, had evolved over millions of years in a world where the only light after sunset was firelight and moonlight, both of which were too dim and too red-shifted to significantly affect the clock's timing. The blue spectrum light of modern device screens, experienced in the hours before bed, suppressed the release of melatonin, the darkness-triggered hormone that signaled the circadian clock that night had arrived, and delayed the clock's timing in a way that made it more difficult to fall asleep at the desired time. The magnitude of this effect was quantified in a study published in 2014 by the Harvard sleep researcher Charles Czeisler and his colleagues, who had subjects read for 4 hours before bed on either an iPad or a printed book over a period of 2 weeks. The iPad readers showed substantially delayed melatonin onset, took longer to fall asleep, had less REM sleep in the early part of the night, and reported feeling more drowsy the next morning than the book readers, even when total sleep time was controlled. The implication was that the habitual use of screens in the hours before bed was creating a systematic circadian disruption that was additive across days and weeks, producing the kind of chronic circadian misalignment that shift workers experienced, but experienced in this case by anyone who routinely used a screen before bed. The shift work analogy was important because the health consequences of shift work, the long-term disruption of the circadian clock that occurred when people regularly slept and woke at times that were misaligned with their biological rhythms, were among the most well-documented in occupational medicine. Shift workers showed elevated rates of cardiovascular disease, metabolic disorders, certain cancers, and reproductive problems, and the epidemiological evidence for these effects was strong enough that the International Agency for Research on Cancer had classified shift work involving circadian disruption as a probable carcinogen. If the screen use patterns of modern adolescents and young adults were producing circadian disruption of even half the magnitude of shift work, the long-term health consequences could be substantial. The adolescent population was of particular concern. Adolescence was characterized, for biological reasons, by a natural shift toward eveningness, a delay of the circadian clock that made teenagers naturally inclined to stay up late and sleep late. This shift was driven by hormonal changes that altered the timing of melatonin secretion, and it was a genuine biological phenomenon rather than a behavioral choice, as demonstrated by studies showing that it occurred in adolescents across cultures and was observed in other animals during the equivalent developmental stage. The school schedules of most industrialized countries which required adolescents to begin school at 7 or 8 in the morning, times that were earlier than the biological rhythms of most teenagers could comfortably accommodate, were creating a systematic sleep deprivation in a population for whom sleep was particularly important, because adolescence was a period of intense brain development and synaptic pruning in which sleep appeared to be specifically critical. The research on adolescent sleep deprivation produced some of its most striking findings in studies of academic performance, mental health, and risk behavior. Students in schools with earlier start times showed lower academic achievement, higher rates of depression and anxiety, more drowsy driving accidents among those who drove, and higher rates of substance use than students in schools with later start times, even after controlling for socioeconomic factors and other potential confounds. The American Academy of Pediatrics published a recommendation in 2014 that middle and high schools should not begin before 8:30 in the morning, based on the accumulated evidence of the consequences of early start times for adolescent health and performance. The implementation of this recommendation has been slow, because school start times are embedded in complex logistical and economic constraints, but some districts have made the change, and the before and after studies have generally confirmed the predicted benefits. The broader social question, raised by the evidence of widespread sleep deprivation, the question of what, if anything, should be done about it, was one that the sleep science community approached with increasing urgency in the early decades of the 21st century. Matthew Walker's 2017 book Why We Sleep, which synthesized the previous decades of sleep research for a general audience and made the case for sleep's importance in uncompromising terms, became a bestseller in a way that no previous sleep science book had been. Walker's argument that the sleep crisis was a public health emergency of the first magnitude, comparable in its long-term health consequences to smoking or obesity, was controversial among sleep researchers, some of whom felt that his presentation of the evidence was insufficiently nuanced. But it connected the findings of the laboratory to the concerns of ordinary people in a way that generated unprecedented public attention to the issue of sleep. The controversy over Walker's book was itself instructive, because it illustrated the gap between the state of the science and the state of public communication about the science. The evidence that chronic sleep deprivation had serious health consequences was genuinely strong. The evidence that the specific mechanisms Walker described, the connections between sleep deprivation and Alzheimer's disease, cancer, cardiovascular disease, were causal in the specific ways his book implied, was in some cases less clear, because the epidemiological data could not always distinguish between sleep deprivation causing disease and disease causing sleep deprivation, or between sleep deprivation and the underlying conditions, depression, anxiety, metabolic disease, that often accompanied it. These distinctions mattered for the precision of the claims being made, even if the general message that sleep was seriously important for health and that most people were getting less than they needed was broadly correct. The 21st century also brought new understanding of dreams, the subjective dimension of sleep that had fascinated humans for as long as they had been capable of reflection, and that had remained, despite the discovery of REM sleep and the identification of its neural correlates, largely mysterious in its specific content and meaning. The Freudian theory of dreams, that they were disguised expressions of unconscious wishes, their content distorted by a censoring mechanism that made the wish acceptable to the sleeping mind, had dominated popular and clinical thinking about dreams through much of the 20th century, but it had received little empirical support from the laboratory and had largely been abandoned by sleep researchers by the end of the century. The activation synthesis theory proposed by J. Alan Hobson and Robert McCarley in 1977 offered a radically different account, that dreams were the brain's attempt to make sense of random neural activation generated by the brainstem during REM sleep, the forebrain constructing the best narrative it could from the random signals it received, which was why dreams had the specific characteristics they had, the mixture of familiar and strange, the narrative logic that dissolved on waking, the emotional intensity combined with lack of critical self-reflection. The activation synthesis theory was also not entirely satisfying, because it implied that dreams had no specific function or content, that they were simply the epiphenomenal product of random neural noise. But the increasing sophistication of dream research in the early 21st century suggested that dream content was not random, but was specifically related to the concerns and preoccupations of the dreamer's waking life, to the experiences and emotions of the preceding days, to long-standing anxieties and unresolved conflicts, and to the material that was being consolidated and processed in the memory systems during sleep. The researcher Erin Wamsley at Harvard demonstrated in a series of elegant experiments that people who were learning a new spatial navigation task showed significantly more task-related dream content during subsequent sleep than people who had not been doing the task, and that the frequency of task-related dream content was specifically correlated with how much their performance improved after sleep. This was a striking finding. The dream content was tracking the memory consolidation process, appearing in the subject's awareness as a byproduct of the neural reactivation that was consolidating the task memory. The dream was not merely a random narrative, it was, in some sense, a glimpse into the memory processing that was occurring. The relationship between dreams and memory reactivation was confirmed by studies using newer neuroimaging techniques that could track the specific patterns of neural activity during sleep and identify when those patterns corresponded to the patterns that had been established during waking learning. In 2007, researchers at MIT, led by Matthew Wilson, used electrodes implanted in the hippocampus of rats to record the activity of specific neurons during maze learning and then during subsequent sleep. They found that the same sequences of neural activity that had occurred during maze navigation were replayed during slow-wave sleep, in compressed, faster form, but in the same sequence as if the hippocampus was running a rapid movie of the day's experience. This neural replay during sleep was the mechanistic basis of memory consolidation, and it demonstrated that the sleeping brain was not merely storing memories passively, but was actively processing them. Human neuroimaging studies conducted in the following decade provided evidence for similar replay during human sleep, and also for a remarkable phenomenon, the forward planning that occurred during sleep. While the replay of past experiences during sleep consolidated the memories of what had happened, the sleeping brain also appeared to engage in prospective processing, simulating possible future scenarios that drew on the consolidated past experiences. The specific form that this prospective processing took in consciousness was what people experienced as dreams about future events, the planning dreams, the anticipatory dreams, the rehearsal dreams that many people reported, which seemed to involve simulating possible future scenarios in a way that prepared the dreamer for the situations they anticipated encountering. The simulative function of dreaming, the idea that dreams served as a kind of virtual reality simulator in which the brain rehearsed and prepared for waking life challenges, was proposed most comprehensively by the Finnish neuroscientist and philosopher Antti Revonsuo in his threat simulation theory. Revonsuo argued that dreaming had evolved as a mechanism for rehearsing responses to the threatening situations that were common in the ancestral environment, that the specific content of dreams, their tendency toward threatening scenarios, their emotional intensity, their simulation of physical challenges, was the product of natural selection favoring individuals who rehearsed threat responses during sleep and were therefore better prepared to respond effectively when similar situations arose in waking life. The threat simulation theory had supportive evidence from studies of dream content. Threatening events were indeed disproportionately represented in dreams compared to their frequency in waking life, and from cross-cultural studies showing that people in environments with higher levels of physical threat showed more threatening dream content than people in safer environments. But it was not without its difficulties. The majority of dreams, even if emotionally intense, were not straightforwardly threatening, and the theory's emphasis on threat at the expense of the full range of dream content seemed incomplete. A broader version of the simulative account, the social simulation theory proposed by Revonsuo and Katja Valley, argued that dreams simulated not just threatening situations, but the full range of social and emotional scenarios relevant to the dreamer's life, providing a rehearsal space for the complex social cognition that characterized human life. On this account, the specific content of dreams, the social interactions, the emotional encounters, the navigation of complex interpersonal situations, was the product of the brain's offline simulation of the social world it was embedded in, a simulation that served to maintain and develop the social skills that were critical for survival and reproduction in the fundamentally social species that humans are. As the third decade of the 21st century progressed, the understanding of sleep that had been built over the previous century, from Berger's EEG through the discovery of REM sleep, through the identification of the glymphatic system and the genetics of sleep need, was being integrated into a picture of extraordinary coherence and depth. The picture it presented was one in which sleep was not a single thing, but a complex state with multiple distinct phases, each serving specific functions that were integral to the biological and cognitive functioning of the organism. The slow-wave sleep of the early night was the period of deepest physical restoration, of glymphatic waste clearance, of growth hormone release, of the hippocampal replay that consolidated declarative memories. The REM sleep of the later night was the period of emotional memory processing, of creative integration, of the maintenance of the neural circuits that supported emotional regulation and social cognition. The cycling between these two states, the approximately 90-minute architecture that Dement had established, was not arbitrary but was the product of a specific neural orchestration in which the timing of each stage's appearance was coordinated with the overall trajectory of the night, ensuring that the brain received the appropriate mixture of each kind of processing in the appropriate sequence. The circadian clock, the molecular timekeeper in the suprachiasmatic nucleus, driven by a set of interlocking molecular feedback loops that had been identified at the level of individual genes and proteins, coordinated the timing of this architecture with the external world, ensuring that the deep, slow-wave sleep occurred in the first half of the night, and the REM sleep accumulated in the second half, and that the entire cycle was timed to the cycle of the Earth's rotation in a way that aligned the body's physiological processes with the predictable variation in the environment. The molecular details of this clock, its architecture of interlocking transcription-translation feedback loops, its entrainment by light through the retinohypothalamic tract, its coordination with peripheral clocks in virtually every organ of the body, had been worked out in sufficient detail to earn the Nobel Prize in Physiology or Medicine in 2017 for the researchers Jeffrey Hall, Michael Rosbash, and Michael Young, who had done the foundational molecular genetic work in fruit flies and mice. The Nobel Prize for Circadian Clock Research was, in a sense, the formal recognition by the scientific establishment that the biology of sleep and its timing was now understood at a level of mechanistic depth that had seemed impossibly remote when Kleitman and Asarinsky were watching the eyes of sleeping subjects twitch in their Chicago laboratory in 1953. The genes had been identified, the proteins had been characterized, the neural circuits had been mapped, the health consequences of their disruption had been quantified, the pharmacological targets had been identified, and, in some cases, drugs developed to act on them. And yet the central mystery remained. Not the mechanism was known in extraordinary detail. Not the functions. Multiple functions had been identified and at least partially understood. The mystery that remained was the deepest one. Why, of all the possible ways that biological evolution might have organized the relationship between activity and rest, had it arrived at this particular solution? Why sleep? Why this specific, organized, architecturally complex state of unconsciousness, with its specific stages and its specific cycling and its specific EEG signatures and its specific muscle paralysis during REM, rather than some other arrangement that might have served the same functions with less vulnerability and less time cost? The question was not merely academic. It was the kind of question that, when answered, opened entirely new windows into the nature of the biological systems involved. The kind of question that had motivated the sleep researchers of the 20th century, and that was motivating their successors in the 21st. If the function of sleep could be fully understood in evolutionary terms, if the specific adaptive advantages of sleep in its specific form could be identified and quantified, then it would be possible to understand what was at stake in the current epidemic of sleep deprivation in a much deeper way than the existing epidemiological evidence allowed. The question that the ancient Egyptians had answered by postulating the nightly wandering of the BA, that the Greeks had answered by postulating the cooling of digestive vapours, that the medieval physicians had answered by postulating the withdrawal of vital spirits from the outer senses, the question of what happened when the eyes closed and consciousness faded and the body stilled and the night began, had been answered in its mechanistic details with a thoroughness and a precision that none of those ancient thinkers could have imagined. The brain did not cool. The spirits did not withdraw. The bar did not wander. Instead, something happened that was in its own way as extraordinary as any of those ancient explanations. The brain entered a state of organized, purposeful activity that was simultaneously unconscious and intensely busy, cycling through stages that each served specific functions, clearing its waste and consolidating its memories and processing its emotions and simulating its future, maintaining the biological systems on which waking health and cognition depended, doing the work that waking could not do and that could not be left undone without consequences that accumulated across days and weeks and years until they became visible as disease. The person lying in their bed, right now, breathing slowly, their eyes moving in the darkness beneath their closed lids, their muscles still, their conscious self absent, is doing something that 4,000 years of human inquiry have worked to understand, and that is now understood in more detail than any previous generation could have dreamed. They are not doing nothing. They are not merely resting. They are engaged in the most complex maintenance activity that biological systems have evolved, an activity so fundamental to everything that happens in waking that its absence is incompatible with health, and whose presence is so taken for granted that most people go their entire lives without wondering what it is. Now you know. The brain cycles, the waves rise and fall, the memories consolidate in the silent hippocampus, passed like handoffs between neurons firing in the familiar sequence of the day's learning. The glymphatic channels dilate, and the fluid moves, and the toxic proteins that accumulated during the day are carried away. The emotional memories of the week are processed in the specific neurochemical environment of REM sleep, their charge reduced, their information preserved, their integration with the fabric of the self completed. The circuits that will generate tomorrow's creativity and tomorrow's judgment and tomorrow's capacity for the full range of human feeling are maintained by the activity of the sleeping brain, which is not asleep in the sense that word implies, dormant, still, absent, but is alive in the specific way that it needs to be alive to make waking life possible. The ancient Egyptians were wrong about the mechanism, but they were right about one thing. Something happens in the night that is connected to everything that happens in the day. The BA does not wander, but the brain does something organized, something purposeful, something whose importance to the life of the waking person is not optional, but fundamental, something that is happening to you right now, something that has been happening to every human who has ever lived, every night of their lives, without their understanding and without their permission, the most universal and most intimate experience of the human condition, the nightly maintenance of the self. The science knows now more of what it is. The question of why it is, the deepest question, the evolutionary question, is still being answered in laboratories around the world, in studies that will be published in journals that will be read by researchers who will follow the thread further than it has been followed before. And while the researchers work, and while the science advances, and while the questions accumulate and the answers accumulate and the understanding deepens, the brain sleeps.